we have this skier drag up the slope of angle theta with frictionless slope going up, and the mass is given, theta is given, the acceleration is given. You want to find what is the tension force. So in order to do that, we need to draw a Freebody diagram for the person. There's tension force acting on the person, W, which is mg, downward, and normal force in that direction. Because it has acceleration in the parallel to the ramp, it is best to take x direction that way. So we take this as x direction, and perpendicular to that as y direction. And then tension will be in the x direction, and normal force will be in y direction because it is perpendicular to the slope, and W will be straight downward, mg. Right? And this angle here is equal to this angle, because if this is angle to the horizontal, if you look at the sides of this angle, one side of this is perpendicular to the weight, horizontal side is perpendicular to the weight. This side is x-axis, is perpendicular to the y-axis. So these two angles are the same. So if this is theta, this is also theta. Right? This is my Freebody diagram. The acceleration is also in x direction. So I usually put the acceleration also there too, but not from here because it's not a force. I don't put it at this. And this is the person, right? So next thing to do is to apply Newton's law in both directions. Sum of fx equal to max, and sum of fy equal to may. And a is in the x direction, so ay is 0, but ax is just magnitude a. So sum of fx, how many x components do we have? See, n doesn't have
a question. Isn't there a magnitude for the y, for the ay?
Ay is 0 because it is in for this coordinate system, because a is in the x direction, ay is 0.
Gotcha.
Right? In this case. That's why I'm saying this kind of coordinate system is more convenient than normal horizontal and vertical coordinate system.
Can I do horizontal and vertical?
Yes, you can. I'm going to show that.
Oh, okay.
Yeah.
Gotcha.
But see how much different it gets. So let's write the first one. So these are our two equations. The first one becomes all the x components, which is n doesn't have x component, right? X component of t becomes just magnitude t, right? And x component of mg comes with sign because it is not adjacent to theta, but it is in the negative x direction. So it becomes negative mg magnitude times sine theta. Is that clear? Because it's the y component is adjacent to theta. The x component is not, so we use sine. But it falls in negative direction, so we can negative sine times magnitude. This is all the x components, n doesn't have x component, is equal to ma. So that directly gives you t, right? The t becomes mg sine theta plus ma. And you have all of these. You have mass, you have g, you have theta, you have a. You can calculate t. If you want, you can factor m. And then, what is the normal force? You can also calculate normal force from the other equation. So this one gives you that, and this one gives you sum of fy. T doesn't have y component, sum of fy, n has y component equal to its magnitude, so n. And mg has a y component negative of magnitude times cosine theta, equal to 0, because this side is 0. So normal force is also equal to mg cosine theta.
I have a question.
Yeah.
Is it always going to be easier to shift your coordinate system like that?
When you have an acceleration,
yes,
you put x or y direction in the direction of acceleration. That makes it a lot easier.
Okay, that makes sense.
Yeah. So now you see that? Now let me do it the other way. If I take the horizontal and vertical as the x and y coordinate, let's see what changes. And then t will be in which direction? T will be at angle theta, right? This is t. The normal force is also perpendicular to the rope, which is in this direction at angle theta. But the weight is in the negative y direction, right? And the acceleration is also makes an angle theta like that. Is acceleration. So acceleration has two components. T has two components, N has two components, but W has one component, the weight. So that right now you see that it's makes it a lot more complicated because you have to calculate components for three vectors versus calculating components for one vector. But let's do that, see what happens. Sum of fx equal to max gives you this. T cosine theta, right? I write in terms of magnitude and direction. X component of t. T cosine theta. What is the x component of n? It is negative, but because it's not adjacent, negative n sine theta, right? And W doesn't have x component, but that is equal to a magnitude, m times a magnitude times cosine theta. Right? So one equation becomes like this. And it involves t and n. And we are not interested in n right now. We want to find this t, right? All right. So this is one equation. And then the second equation will be sum of fy equal to may. Sum of fy means all the y components. What is the y component of t? T sine theta. What is the y component of n? N times cosine theta, right? Positive, and this because it's adjacent. Minus mg equal to mass times y component of acceleration, ma sine theta, right? So you see, this is another equation. Right? If I want to find t, I need to somehow eliminate n. Everything else is known, right? I need to eliminate n between these two equations and then solve for t. Let's eliminate n. There are many ways to do that, but let me one of them. So n in here becomes, if I move this over, becomes t cosine theta minus ma cosine theta divided by sine theta. So I can put now here, put this n in this equation. So t sine theta plus n cosine theta becomes t minus ma times cosine theta divided by sine theta times another cosine theta, which becomes cosine square theta, right? This one is for n multiplied by cosine theta. So we have t sine theta, n cosine theta minus mg equal to ma sine theta, right? And now if I multiply everything by sine theta to get rid of this denominator, I multiply everything by sine theta, become t sine squared plus t minus ma cosine squared theta minus mg sine theta equal to ma sine squared theta. Right? And now, what do I have for t? So t sine squared plus t cosine squared. That's just t, right? T equal to, I move everything to the other side. And then you have ma cosine squared comes here becomes positive, and then you have ma sine squared, right? You get ma. Do you see that? You have negative ma cosine squared. Here you have ma sine squared. If you move this over, you get ma cosine squared plus ma sine squared becomes ma. And then you have mg sine theta. Which is the same as what we had in here. And you see how much more work is there.
My old physics teacher never taught us that way, and I really wish he did. Go left.
You can do it both ways, but it is always, this shows the fact that the coordinate system, choice of coordinate system does not affect the result. This is the physical result. You have t equal to this expression. There's no coordinate system in here, right? These are all in terms of magnitude of the vectors. Magnitude of acceleration, magnitude of g, m, and sine of the angle of the ramp. There's no coordinate system. If there's no coordinate system effect in this equation, this should not depend on your coordinate system. So if you take it that way, it comes up the same. Take it this way, it comes up the same here. But then we haven't figured out n yet, because we now need to put t in here. Say t minus, let me do that too, t minus ma, because m becomes mg sine theta, and sine theta cancels. See, t minus ma is mg sine theta, and then n is equal to t minus ma, which is mg sine theta divided by sine theta, goes away, becomes mg cosine theta. But you see that they are all the same as before. But look how much more work it takes. Of course, because I knew the answer, I did it in a way to get to the answer fast. But if you don't know what the answer should be, you may do a lot of more calculations to get to the answer and simplify the answer to this. So the choice of coordinate system doesn't affect the final result, but some coordinate systems are more convenient to use than the others. So it is up to you what coordinate system to choose. But choose one that is more convenient. In this case, if you have an acceleration, put the acceleration in the direction of a coordinate system. This is very important. If you don't have an acceleration, the choice of coordinate system is not, doesn't matter that much, but still, you should put the coordinate system in the direction of most of the forces. So for example, here, we have, even if you don't have acceleration, you have tension here, normal force here. If you take x this way, y that way, you have two forces in the direction of the axis. Still, that choice of coordinate system is easier.
Can you do this when you have friction and stuff?
Yes, especially for friction. Again, force of friction is in the direction of motion,
wow.
right?
Yeah.
Again, that way is always better. If you have, especially if you have the acceleration. All right?